Hello everybody, my name is Amanda. I'm from University of Campinas in Brazil. I will present to you my work on the improved version of the fuzzy set-based evolving modeling with multitask learning. This work was conducted in collaboration with my PhD supervisor, Fernando von Zube. We will start with the introduction. In this work, I will talk about the evolving fuzzy rule-based systems. In this approach, the learning mechanism is executed online in response to the input data stream. So the creation, update, and removal of rules is managed automatically by the model. The output predicted by each rule is calculated as a linear function of the input variable and the parameters of the consequent part of the rules, represented by theta. The final output is the weighted average between the local predictions provided by the rules and the input variables phi and degree. But how these parameters theta regarding the consequent part of the rules are calculated? So considering the matricial form of the input-output dataset associated with each rule, we seek the solution of the optimization problem that minimizes the empirical loss by means of least squares regression. In the traditional evolving fuzzy rule-based algorithms, the definition of the parameters of the consequent part of the rules is executed by each rule independently, with no information shared among the rules. Recently, we proposed a new algorithm called fuzzy set-based evolving modeling with multitask learning that we will call as FBIM-MTL, that was the first to assume that what is learned by a rule can be useful somehow for the learning process of the other related rules by using multitask learning. So as a complement to the empirical loss, a regularization term represented by omega was added to encode the structural relationship among the rules. With all these theoretical aspects set up, we proceed to the algorithm introduced in this work. We propose here two contributions to our previous work. Both regard the definition of the parameters of the consequent part of the rules. The first contribution concerns the first term, the empirical loss considering all rules, while the second contribution regards the regularization term. Starting with the first contribution regarding the empirical loss, traditionally, all the samples assigned to a particular rule receive the same relevance when calculating the consequent parameters using least squares regression, despite holding different phi degrees to the information granules. In this work, to calculate the prediction loss, we take into account the similarity between a sample designed to a rule and its mean point, considering all samples belong to that rule, as expressed in equation 11. If we calculate the similarity of every sample belonging to the rule, we can create the diagonal matrix W, as in equation 12. We consider this matrix W as the weight of the weighted least squares method adopted in this paper. So the prediction loss is calculated according to equation 14. Instead of considering all samples with the same relevance, now we adopted different penalty criteria according to the degree of similarity of the sample to the mean point of the rule. Now we proceed to the second contribution regarding the regularization term of the optimization problem. In this paper, we introduce a generalization of the sparse structure regularized learning with least squares loss. The foundations of this method I will explain next. Considering a trapezoidal approach for the antecedent part of the rules, the similarity measure between two rules is defined as in equation 17. Calculating the similarity measure between every pair of rules, we obtain the similarity matrix of equation 19, which is symmetric and may be directly interpreted as the pairwise dependence among the rules. The approach adopted in this paper, which is a generalization of our previous work, uses the information about the similarity measure among the information granules to create a graph, where each rule is a node and an edge connects two nodes if their corresponding rules are related. In order to represent this graph, we use a matrix that we call matrix G. The approach introduced in this paper employs directly the information obtained by matrix S to obtain matrix G, avoiding the binarization routine adopted in our previous work that resulted in loss of information and demanded an extra threshold parameter. The matrix G is formed by several column vectors representing the set of edges in the graph. If the similarity measure between a pair of rows is greater than 0, then the corresponding column representing the connection between these two rows will contain the value of the similarity at the corresponding rows, and the value 0 for the remaining. As an example, given this illustrative similarity matrix S, the corresponding matrix G representing the complete graph is expressed by equation 26. So the final regularization term, represented by equation 27, penalizes the Euclidean distance between all pairs of connected tasks in the graph according to their similarity measure. Finally, the regularization term implementing the multitask learning perspective is expressed by equation 29. It forces the related tasks informed in matrix G to exhibit a low Euclidean distance between the corresponding pairs of columns of matrix theta. In our previous work, there were two additional regularization terms that forced the elements of matrix theta to approach 0 whenever the impact on the empirical loss was reduced. In this generalized version, they were discarded without compromising the quality of the results and leading to the elimination of two additional parameters. The final expression of the optimization problem is given by equation 30. To solve this optimization problem, we adapted the accelerated gradient method. The new gradient is defined by equation 32, where the partial derivatives for each rule is defined by equation 33. We conducted a series of 3 computational experiments. In all of them, the algorithms were evaluated using the root mean square error, and the values provided by all the time series were normalized in the interval 0-1, considering the trained data set. We'll start with the first experiment. The goal is to predict one step ahead monthly precipitation in 86 geographical locations in South America. The dataset contains data from 1917 to 2016, resulting in 1,200 data points each. The original dataset is used for training, while the test is conducted with the flipped time series. This table provides the performance of all FBIM versions. The first FBIM without the multitask learning strategy, the FBIM MTL with the multitask learning strategy, and the 2 new versions proposed in this paper. Version 2.0 refers to the generalization of the multitask learning approach, and the version 2.1 builds on the improvements achieved previously and introduces the weighted least squares extension. We can see here the incremental improvement achieved in the root mean square error by the new versions proposed in this work, while keeping the same number of rows. We proceed now to the second experiment. The goal is to predict one step ahead of monthly temperatures for the cities Death Valley, Ottawa, and Lisbon. The table shows the performance of FBIM-MTL family of algorithms against other contenders in the literature. The new versions of FBIM-MTL can further improve the performance of the original algorithm, outperforming all the other contenders. We finally get to the last experiment. The goal is to predict one step ahead of hourly wind speed during the year of 2012 in the 3 largest wind farms in the United States. For each wind farm, 5 well-distributed turbines were analyzed, totalizing 15 time series. This table presents the result of the statistical analysis we conducted. The original FBIM-MTL obtained the 4th position in the table. With the improvements of version 2.0, that means the generalization of the multitask learning approach, we achieved a slightly better result, but yet behind the performance of algorithm EPL-KRLS. It was only with the adoption of the weighted least squares method in version 2.1 that FBMTL was able to obtain the best performance compared to the other contenders, being statistically superior to the last 4 algorithms. This figure presents the predictions for 2 intervals of one of the time series, comparing the performances of the original FBMTL and its extended 2.1 version. We can note the more accurate prediction provided by the yellow line representing version 2.1. To illustrate the behavior of the improved version of FBMTL, I will present a series of figures illustrating the evolution of the algorithm along time for one of the time series. Here I show the distribution of the information granules along time. At the beginning of the time series, there are 3 dispersed granules. Many periods after, there is the creation of new information granules more specialized in specific regions. Finally, near the end of the time series, the granules are more equally spaced. Here, we have the corresponding graphs obtained from the degree of similarity among the rows for the same time instance, illustrating the operation of the generalized version of the multitask learning approach. The graph's nodes correspond to the center of the granules, and the width of the edges is proportional to the similarity between each pair of connected rows. Now I present the corresponding matrix G for the 3 time instance, based on the similarity measure among the rows. The number of columns of each matrix corresponds to the number of connected rows in the graph. Now I illustrate the weighting policy of the weighted least squares approach, considering the same time instance from before. We plotted some of the samples with their corresponding weights. To samples located far from the denser region, lower weights are assigned, and as a consequence, they contribute less in the prediction loss. To conclude, we propose here an improved version of the fuzzy set-based evolved modeling with multitask learning. As the first contribution, we extended the original least squares optimization to a weighted least squares, raising the impact of samples located at denser areas when compared with samples situated further away. As a second contribution, we also developed a generalization of the regularization term that encodes the roles' structural dependencies. In this new formulation, we define a real-valued matrix representing the fuzzy relationship among the roles, avoiding the loss of information that the previous binarization routine brings, and also eliminating a threshold hyperparameter. Lastly, we eliminated 2 extra regularization terms from the optimization problem, thus bringing compactness to the model without compromising the performance. All the 3 conducted experiments evidenced the benefits of the contributions presented in this paper. So that's all. I would like to thank you for the audience and hope to see you again next time.